SD cards are slow, and NVMe drives are blazing fast. So today, we're fixing that. I will show you how to stop letting your Raspberry Pi be held back from SD cards and instead install, boot from, and unleash 20 times performance gains that comes with an NVMe drive. That being said, let's go engineer some stuff. For our NVMe drive setup, I'm using the official Raspberry Pi M.2 HAT Compact. This way it fits nicely in the official Raspberry Pi 5 case and gives us a very clean setup to work from. The NVMe is the official Raspberry Pi 512GB model in the 2230 form factor, as the compact M.2 HAT doesn't fit any other size drive. To make room for installation, we'll pop the lid off the Pi's case. We will also need to unplug the fan header so that's not dangling about during the install. Unboxing the package the NVMe hat comes in, we have the hat itself in a static silver bag and a plastic baggie with all the spacers and screws we're gonna need. Let's line up our 3 standoffs, and using the short screws to get the standoff screwed down into place. Take the hat now and line it up with the 3 standoffs, and we will need to push the 40-pin connector all the way down into our 40-pin connector on the Pi. Make sure there's no space between them for a good firm connection and that the screw holes line up as expected. Take the other 3 remaining short screws and use those to secure the hat to the Pi. For the ribbon cable, we'll need to open the ribbon cable holder. You'll know it's open when the brown latch is sticking up. Gently insert the ribbon cable. Make sure the copper contacts face inward towards the USB and Ethernet ports. Time to plug in our NVMe drive into the PCIe connector on the hat. Using the silver colored screw latch, we will first screw that into place and then latch our drive into place with the notch. Lastly, let's get our case reassembled. We'll plug the fan header back in, plug the first part of the case back, and then the top part of the case, and we are good to go to start playing with this NVMe and seeing what blazing fast speeds it has to offer. Before we can get those blazing fast speeds, we're going to need to update our Pi. First step will be to make sure the latest packages we need are installed, and then we can check the EEPROM. The EEPROM is what stores the bootloader firmware that will recognize our NVMe drive. We can see we are running the latest version and don't need to update, so we can move to making sure our NVMe drive is recognized. Don't worry, if you do need to update your EEPROM, I'll flash the steps for that on the screen right now. And we can tell that the NVMe drive is recognized with list block device and using fdisk. Our list block devices command will return the full name of the drive and its size, and it's important to remember I installed a 512GB drive, but the actual capacity will be lower, in this case about 477GB. And our fdisk command also shows this size where the block device is stored under dev NVMe 0N1. It's important that we remember this, but just because we can see the disk doesn't mean we are done yet. For our NVMe to actually be usable, we're going to create a disk partition, create a file system, and create a mount point for the drive. To start the partition process, we will run fdisk with the path to our drive, and you'll see you'll be greeted with the message that it created the MBR disk label automatically, but we will be changing this to use the newer GPT standard, as MBR is really only used on older systems. Think the 20-year-old computers your grandma still uses. Then setting a partition number 1, the default is fine because we only have 1 partition on the NVMe and use the whole drive. Keep the default values for first and last sector, which refer to where Linux starts reading data from on the drive. No need to change that. By typing W, we will write all these changes to the NVMe drive. Now when we do lsblk, we see our NVMe has partition 1 on it, which is exactly what we want to see at this point, and then we can move on to creating the file system. For the file system, we will use make file system command with sudo mkfs.ext4-l, specifying an easy-to-use label for our drive. You can call it whatever you want. I just called it NVMe storage. The last part of the command is specifically the disk partition path we created in the previous step. So now with our disk partition and file system created, we still have to mount the drive to be able to use it. Let's make a directory under mount. This is where drives get mounted to, typically on Linux. We'll call it NVMe, and if we ls on it, it'll be empty right now because we just created it. Then let's do mount with the path to our drive partition that we noted from the previous step, and then the path to where we actually want to mount it, which in our case will be mount NVMe. And using df and grepping for NVMe, we can see the drive is mounted and has about 445GB of storage free for us to use. But if we cd to our mount directory and try to write a test file, we get permission denied. This is because Linux doesn't know who should be allowed to use this drive, and we have to tell it. To tell it that, by doing sudo chown or change ownership, your username, in my case sgr, and the path to our mount point at mount NVMe, our user now has full read and write access to the drive. Creating our test file now and catting the content shows us hello world, and we can read and write to the drive, no problem. Now, since it'd be pretty annoying to have to constantly set up this mount point every time we started the Raspberry Pi, let's set it up to do it automatically for us. Sudo block ID will give us a bunch of identification info for our various block devices, and the one we want is our NVMe. For our purpose, we only care about the UUID and the type, so make sure to write those down for the next step. And now with our UUID and type, let's edit the fstab file, which in Linux controls how disks are mounted automatically when the system boots. And we should only see 2 entries in fstab, one for Raspberry Pi's firmware and the other for the Sdcards file system. For our entry, we will use the UUID we wrote down earlier, the mount location we made in the previous steps, mount NVMe in our case, and the file system for us will be ext4. Now, the rest of the options you see, default tells to include standard file system options. We don't really have to worry about that too much. Auto is what automatically mounts the drive. Users tells Linux any user can mount or unmount the drive, which again is why we saw file permission errors previously before changing ownership. Read-write allows read and write access. No fail means that if the NVMe drive fails for some reason, the system will still boot, it just won't mount the NVMe drive then. And the last 2 zeros tell Linux don't dump the contents of the drive and don't check the drive health on boot up, which can add to startup times. We don't really need to do that for this. Let's write those changes then. And catting out fstab file shows our new entry got added. And let's prove it works by rebooting the Raspberry Pi. One reboot later now, back on the Pi, we can list the mount location of our NVMe since it was automatically mounted at boot, and our test.txt file is still accessible and still says hello world as it should. The easiest way to get our NVMe bootable is to clone our SD card to the NVMe. And thankfully, there are a few tools, Raspberry Pi Clone, that makes that a very easy process. We'll start by downloading Raspberry Pi Clone. Don't worry, I will leave a link to this in the description below. Running Raspberry Pi Clone with sudo, let's point it to our NVMe drive block device, NVMe 0N1. And since we already have the drive mounted as storage, we will say yes to unmounting. We are given one final confirmation that this is the disk we want to clone to, which we will again say yes to. And it will start going through the cloning process, which takes a couple of minutes to complete. At the end of the process, it will ask us to hit enter, and now we have an exact clone of everything that was on the SD card now on our NVMe. But we still do need to change the boot order so that the Raspberry Pi chooses to boot from the NVMe first instead of prioritizing the SD card to boot from. To change the boot order, let's head into Raspberry Pi config, then advanced options, A4 for boot order, and we will want option B2, which will make it so the NVMe is the default boot device. After rebooting our Raspberry Pi, we can confirm the boot order has indeed changed, prioritizing booting from the NVMe drive now. What's cool is we can further verify it's booting from our OS from the NVMe because list block devices shows the root file system and boot firmware all located under NVMe 0N1. Find mount also is really helpful, honestly, at providing this because we can see the mount location is different from the SD card on the left than the NVMe drive on the right. So another way to helpfully show and prove that we're booting from what we think we're booting from. Also, let's keep our NVMe drive as healthy as possible by making sure trim is enabled. By default, we can see trim is active. If for some reason it's not, we can easily start it on boot, start it now, and then check again that it's running as expected. Now, if we really want to push our NVMe speed to the limit, we're going to need to enable PCIe Gen 3. Let's head back into Raspberry Pi config. This is also under advanced options. Option A8, PCIe speed, and yes, we would like to enable PCIe Gen 3, and it will confirm PCIe Gen 3 is now enabled. Yes to rebooting, so the correct interface speeds will be set. Once it's rebooted, we can see a comparison of our PCIe speeds from before we enabled PCIe Gen 3 and after we enabled PCIe Gen 3. Our 5 gigatransfers a second fits exactly with the PCIe Gen 2 speed spec, and our 8 gigatransfers a second fits exactly with the Gen 3 spec for PCIe Gen 3. But how fast were our NVMe and SD card speeds actually? Well, let's go hop into our benchmarks and attach some real-world numbers to all of this. Diving into the benchmarks, first up is startup time. Honestly, there wasn't a huge difference when rebooting the Raspberry Pi between the SD card and the NVMe drive, but we did see slightly faster cold boot times, like when you're plugging the Pi in from a powered off state, which made the system feel a little quicker and snappier. in responsiveness. When I change the block size in these benchmarks, I'm basically changing the type of workload that I'm simulating. The way you can think about it is a 4K block size represents lots of tiny file operations, things like booting the OS, installing packages, and general system responsiveness. This is really what makes a computer feel fast or slow to most of us. 64K represents more of a mixed workload, larger chunks of data, but still realistic for day-to-day activities and workloads. And 1 meg block sizes simulates large sequential transfers, like copying a big video file, a massive database, you name it. That's usually where manufacturers advertise their maximum read and write speeds that you might see online when picking out an SD card or an NVMe drive. So smaller block sizes tell us about responsiveness, while larger block sizes shows us the maximum throughput of the drive. Overall, an NVMe upgrade doesn't drastically change boot time, but if you're working with containers, databases, or other large files and heavy workloads, it makes a huge difference. And who wouldn't want 10 to 20% faster storage? I know I would. That being said, if you found this video helpful, please don't forget to like and subscribe, and if you have any questions, let me know down below. I'm always happy to answer them. And as always, I'm Sam the Engineering Man, and I'll see you all in the next one.